Hi there, welcome to Chapter 4. Chapter 4 is on our measures of variability. So if you recall, we went over measures of central tendency, which is all about capturing that value that best describes an entire data set. We're going to move into measures of variability now, which is often coincides with the measures of central tendency. So first and foremost, let's take a look at, bear with me, not letting me click forward. There we go. So first and foremost, variability is what I consider an umbrella term. So it is what it does is it talks about how scores in a data set or a data distribution are dispersed across that distribution. So how spread out they are or how clustered together they are. So you could have um, you know, a distribution of scores. Ooh, let me go back. Sorry. A distribution of scores that are, let's see here. Let me go to my pen. It could look like this. So as you can see, there's a very small curve. They're very dispersed across. Or you could have a distribution where the scores pile up really high in the middle, and then there's smaller tails. That tail's pretty fat compared to what I was supposed to do. But as you could see, like you could have this wide dispersion of scores, or you can have scores clustering at this peak in one area. That really is variability. Now, variabilities, whenever we calculate variability, there's three types of variability, and we'll talk about what they are. But any value that is a measure of variability has rules or characteristics that we have to abide by. And if you remember these rules, you'll know when you're calculating if you've done something wrong, if you can remember these characteristics or the rules of variability. So variability cannot be a negative no matter what. So if you get a negative value when you've calculated any of the three measures of variability, you know you're wrong. Because variability ranges from 0 to infinity, whatever. 0 meaning there's no variability. No variability means every score is exactly the same, which is very unlikely that you're going to get that. But that's the least that it can be. So either they vary, where the variability is greater than 0, or scores do not vary and it is 0. So as soon as the scores kind of start dispersing away from each other, there is going to be variability. And so therefore you can't have a negative variability at all. That's meaningless, completely meaningless. So let's look at what the three measures of variability are. So if you recall, I had said if I was to ask you what are the measures of central tendency, you should be able to know you need to report the mean, median, and mode. It's the same way with variability. If you're asked what are the measures of variability, you need to be calculating the three measures of variability, which are range, variance, and standard deviation. So I'll never ask you specifically for the range and variance and standard deviation as separate components. I will be asking you for the three measures of variability. So you need to know that that entails those three measures. So let's talk about each of those measures. Starting at the very least explanatory, if that's even a word. Don't judge me if it's not. The you know the range is probably the least used measure of variability, but it's still a very useful measure of variability because especially if we have um, a, a, dis, um, a distribution that is odd or something. Like if we have a distribution, okay, we have an average that's 50, out the scores are between 0 and 60. That tells you that things are pretty spread out. So it depends on if you have like an odd distribution, and sometimes the range is more like a supplemental measure of variability, but it is a useful measure of variability. So you in previous chapters, when we talked about the grouped frequency distribution, you used what was called the real range. Whenever you're asked for measures of variability, you are just going to give the straight up range, just the standard range, which is the largest value minus the smallest value. So you take that higher number and then you subtract the lowest number from it, the very highest minus the lowest number, or largest minus smallest, whatever whatever's easiest for you. And the difference between that is your range. It's just the simplest way of describing how far the scores are dispersed. And it is informative if you have a data set that doesn't have a lot of outliers, meaning there isn't just some random score that is way off um, on its own. So as you can see from this data set, we have these raw scores, 1, 1, 2, 3, 4, and 5. And they're done in order just to make your life easier. So 5 is the highest number and 1 is the lowest number. So 5 minus 1 is 4. Now, it's a little bit trickier when you have negatives. So -2 would be the lowest and +2 is the highest. So here's your highest, right? And here is your lowest. And you want to put parentheses around it because a negative and then another negative is going to make a positive. So negative, you subtract two negatives and it's a positive. So that's why we end up with a 4. So you want to be really careful when you're calculating any kind of negatives, which can occur. So range is very simplistic, very, very simplistic. The easiest measure of variability that we have, just the highest minus the lowest number. So variance is where we start when we're kind of, this is kind of, to me, like a starting point. Standard deviation, our third measure of variance, is ultimately kind of our final answer that we often provide. But variance is just as meaningful, a variance, but we have to have variance to get to standard deviation. So variance in itself is a measure of the average square distance that scores deviate from the mean. So you have the mean here in the middle, and then here's scores that are surrounding that mean, higher, lower, etc. And you're measuring the distance for each one of them. And then, but you're taking the average of all those distances squared. So if you'll notice with the definition of variance, here's the notation, the Greek symbol for a population variance. And you'll notice the squared. That coincides with its definition, the average squared distance. So we have what is called sums of square. That is another notation over capital N, that member population size. The sums of squares is the sum of x squared minus the sum of x total squared divided by n, the population size, and this entire equation is divided by n. So this is one of the errors that I see students make, is taking the sum of x squared minus the sum of x total squared and then dividing that whole thing by n. No, this here is a little fraction that's subtracted from the sum of x squared, and then that whole amount is divided by n. So sums of squares is a notation for sum of x squared minus sum of x total squared divided by n. This is a notation. It's not an equation. It's a notation. So this is specifically for population. That notation, this sigma, lowercase sigma squared, is telling us that's a population variance. It's very important because it's a language. Variance for a sample of scores is S squared. Again, it's variance, there's the squared because it's the average squared distance. Scores deviate from the mean. And again, it's sums of squares, but now we have another notation called DF. And we'll talk about what that means. But df is actually n minus 1. So you would take the entire sums of square, you would calculate this entire equation, and then you would divide that total or that amount, that value that you got for sums of squares, and you would divide it by the sample size minus 1, which is df. And so let's take a look at what df is and why we use df. So df is called degrees of freedom. That's what df is. It's a notation. So we've already added multiple notations to your regime of notations that you need to learn. So degrees of freedom is df, and all it does is it determines the number of scores in a sample that are independent and free to vary. So it's n minus 1. And so basically, if you have a sample, if you took the mean of that sample, that mean is the mean, no matter what. That one score can't vary as long as that sample stays the same. So that's what is really that one is being subtracted for. And is what it does is it kind of addresses the bias or the bias of a variance for samples, or this how the sample does not exactly represent the population. It's taking into account that bias. So it's always used in the denominator of the variance formula for a sample, not the population, because what you're doing is you're accounting for the bias in samples. You don't need to account for bias in a population. And it tells us the estimate of what we would see in that population typically. So if you'll notice, so this is the notation. Here we even have a shortened notation of the equation. In reality, this is the entire equation for s squared. So we like to do little shortened versions, but you need to remember that SS is this equation, that entire equation in the numerator, and DF is that n minus 1 that's in the denominator of the variance equation. So let's kind of take a look at how this plays out. So if this was a population, as you can see, I've already put up at the top that this is a population at the very top there. And so population variance, and we're using the population variance equation. So what we're going to do for the calculations for the sums of squares, which is that SS. First thing we're going to do is find the population size. So here is our original raw data set. So if you count, there's 1, 2, 3, 4, 5, 6 scores. So we have n equals 6. So we know right here, this would be the 6. Then we're going to find just that sum of x, okay? So we're going to add up 85 plus 70 plus 77 plus 92 plus 95 plus 81. Our sum of x is 500. But then we want to find our sum of x squared. So that's basically, we take 85 squared. Oops, let me get out of that. 85 squared, 70 squared, 77 squared, 92 squared, 95 squared, 81 squared. If you were to do those, here's what those squareds would be right here. As you can see, this little column. I don't necessarily recommend you creating a whole separate column for x squared, because a lot can happen with data entry and data error. First of all, you put the 85 squared in and you get the answer, and then you have to write down that answer. And then you go 70 squared, you get that answer, and then you have to write that answer down. There's a lot of room for error. You could write the number down wrong. And then when you enter things back in, you could enter it wrong. So hopefully you have found that exponent, the squared symbol on your calculator, and you know how to work it. And I just put it in as a string. So I put 85 exponent squared plus 70 squared plus 77 squared plus 92 squared plus 95 squared plus 81 squared. And then before I hit enter, I look through to make sure I haven't made any data entry errors, and I hit enter. And that'll keep you from kind of ending up with data entry errors, which is very, very easy to do when you're dealing with large data sets. So then we have our sum of x squared. And so this is one of the reasons why in the beginning of this course, I was emphasizing on the order of operations between sum of x and sum of x squared and sum of x total. So if you'll notice, this sum of x squared, this right here, coincides with this. And then this sum of x total, it coincides with this. So if you just plug it in, there's 500 here. So 42,104 minus this fraction, 500 squared divided by 6. So this is a separate fraction by itself. Once you take that sums of squares, it's 437.33, and you divide by 6. And here is your variance, which is the average squared distance from the mean of the population. So this is where practice is really going to come in handy for you. So let's look at the same thing for variance. So really it's doing the same thing. It says we're doing sample variance. So now we need to use the correct equation and use the correct notation. So S squared is sample variance. It is the same equation except for here in that denominator you have n minus 1. The same data. We have 500 for our sum of x, which is right here. We have a sample size of 6, which you can see is right here. The sum of x squared, as you can see, this 42,104 is right here. And so we can start plugging in. But now the differences for that sample is we need to take account of the degrees of freedom, the 6 sample size minus 1, which is 5. So now that same amount you got originally for the sums of squares is divided by 5 instead of 6. And so our sample variance is 87.47. So is what we would be reporting this as is this, S squared equals 87.47. That would be my final answer for that. Always use the appropriate notation, and it's always rounded to 2 decimal places. That 7 is that second decimal place, and it's rounded appropriately. So those are the measures of variability. Now, the third measure, or those are the first 2 measures of variability. I'm sorry. Now, the third measure of variability is the standard deviation. And this is easy at this point because once you get the variance, it's easy to get the standard deviation. So you calculate the standard deviation by taking the square root of the variance. The standard deviation is the measure of the average distance. It's not a square distance, it's the actual distance, the actual average distance. So is what we do is we take from before, like our variance equation was that lowercase sigma squared. Variance is now just sigma, no squared, for population. And the equation is the same equation as the variance equation, but now a square root over it. And the standard deviation is SD, where before it was S squared. So in reality, and I don't know why it's missing, so SD equals the square root of S squared, that variance. So you're just taking the square root of the variance from your calculations. So let's see how that looks. So that standard deviation of the population, so previously we had calculated it, and for population, our variance, if you recall, was 72.89. Sorry about my writing. So is what we do is now we use our standard deviation equation or standard deviation notation, and we take a square root of that 72.89, and this is now our population standard deviation. So this would be our answer. Standard deviation of the population equals 8.54. Same thing here. Now we're using the standard deviation notation, taking the square root of the original variance, which was 87.47, and we're going to take the square root of that, and our standard deviation is 9.35. And the notation is SD, capital SD. Is what this tells us for the sample is the average distance from the sample mean is 9.3 points. So whatever the mean is here, on average, scores vary around that mean by 9.35 points. That's what standard deviation tells us. It's the most meaningful form of variability that you could calculate. So here's kind of what we're going to be using standard deviation for. So if we have a normal distribution, meaning a symmetrical distribution that could be folded in half with the majority of the data piled in the middle and the tails on the side, we can easily calculate proportions and use predictions, and we know exactly how much, what percentage of scores fall in between standard deviations. And so, like right here on this graph, right here at 0, that basically tells us that's where the mean is. There is no deviation from the mean. If you get a score that is the mean, which I'm going to put here for a sample mean, the standard deviation would be 0. Then at 1 standard deviation above, approximately, let's just say approximately 34% of the data falls here, okay, between 0 and 1. And over here, oops, sorry, 34% falls here. That's very sloppy. So we know that within standard deviations, we have percentages of data if it's a normal distribution of data. And 68% of the data falls within 1 standard deviation of the mean. And so we can start kind of using this to say, what the proportions are in the distributions, where things fall. If you look at this distribution and I took just this left half from the mean and everything below, that's 50% of the data in a normal distribution. And if I took everything from the mean and above, that's the other 50%. So now you can start calculating things like, am I in the 90th percentile in my class, or am I, in the top 10%, which is basically the same thing. Those are the types of things that we're going to be using standard deviation to help us navigate. So it's a very, very useful tool for us to describe distributions. So some things to know about standard deviation, which kind of just goes along with variability as well, but as a reminder, standard deviation is always a positive number. It's 0 means no deviation. Anything above means there is deviation. So standard deviation cannot be negative. So if you ever get a negative standard deviation, you know something's went wrong. You know something is wrong. Sums a square. Back when we were doing sums a square, let me go back real quick. Sums a square, way back here. Okay, here. Sums a square cannot be negative. Absolutely cannot be negative. So this should always end up being a positive value. It can't be negative. So if you get a negative sums of square, you know you've done something wrong. Because sums of square goes into variance, and variance can't be negative, and then it rolls into standard deviation, and it can't be negative. So those are some key things to think about when you're doing these calculations. So standard deviation is always positive. Standard deviation is used to describe quantitative variables. So variables that have number values. You wouldn't use standard deviation for ordinal or nominal data. You would use standard deviation for interval or ratio data. And it is the most informative when it's reported with the mean. So typically, we will have a mean, and then we will report it just like this, m plus or minus standard deviation. So If you took any Psych 101 classes, you know in the population, the mean is 100 for IQ tests or IQ scores on the Stanford-Binet. And so we'll say mu, because it's population, equals 100 in IQ tests. And the standard deviation for IQ is 15. I would report that as 100 plus or minus 15. Even though it's population, you could have it as mu plus or minus standard deviation. That's sloppy, but it could be like that. So this could be the way, so you have your mean first plus or minus 15, which just means 15 varies, is how much things are dispersed and vary around the population mean of 100. It is the most informative when reported with the mean. Kind of does, it's meaningless if it's not reported with a mean. So let's take a look at reporting it with the mean. So in this case, so we had a standard deviation of 8.54 for this population. This was the original data that we just did. That's the standard deviation. If we were to calculate the mean, we've done this before, sum of x divided by n. 500 divided by 6 is 83.33. So here is how we would report that for the population. For the sample, standard deviation was 9.35. The mean is the same because that mean equation does not change between population and sample, but the notation does. That's really, really important to realize. These notations tell us a lot. They tell us whether it's a sample or a population. So when we report it together, we report it just like this. The best way to report those two. So let's kind of think about why we're using variability. So ultimately, variability is going to help us see patterns. So eventually we're going to move towards inferential statistics, and we're going to want to see patterns in data so that we can see whether there's significant differences. We're going to be looking for statistical significance. If we have a high variability where scores are dispersed very widely across that distribution, it's going to be harder to see patterns than if we have a lower variability. So we can kind of see like, okay, we might not have found significance because there was too much variability in our sample, those types of things. So it does help us to see patterns. And then if we can start controlling the variability, that will help us to have a more powerful inferential test to be able to determine whether things are significantly happening or whether there is a significant differences in distributions. So quick and easy as far as measures of variability. Hopefully that was helpful. And if you have any questions, please do not hesitate to reach out to me. Have a great day.